Sir, you can start.
A very good afternoon to all of you. I will invite you, all of you, to the 14th live talk of the MoES webinar series. First of all, I thank Secretary MoES, Government of India, for initiating this webinar series. The Director IITM for giving me the opportunity to give the talk. Desk and computer divisions of IITM and Vinu for all the support. As I mentioned, this is the 14th live talk of the MoES webinar series. We had talks from the other institutes of ocean sciences, atmospheric sciences, polar sciences, ocean engineering, coastal management, and the solid earth core. So we had talks on different fields of all these earth system science subjects. Today, my talk, I will be covering these how an atmosphere and ocean together play an important role in driving the monsoon and its variability. So the title of my talk is Monsoon Variability, Teleconnections and Prediction. These are the outlines of my talk. I'll briefly mention about the Indian monsoon in the context of global monsoon. The different components and or drivers of the Indian summer monsoon will be touched upon. The variability in the Indian summer monsoon rainfall with more emphasis on the year-to-year variability, and the monsoon teleconnections or the remote forcing, especially the El Nino Southern Oscillation and the other teleconnections, and the time varying relationships between all these teleconnections. And I will also touch upon some of the local forcing which happens in the Indian Ocean itself, namely the Indian Ocean dipole, the equino, etc. I will also touch upon the decadal variability or the multi-decadal variability of the ISMR and its predictability and the prediction. This is the first definition of the monsoon, which is based on the seasonally reversing winds proposed by Ramage in 1971. So the region shaded is the region where the prevailing wind shifts by at least 120 degrees between summer and winter, and the average frequency of the prevailing winds will be greater than 40%, and the speed of the mean wind exceeds 3 meters per second. But this wind-based definition is mostly suitable for traders, especially the Arabian traders. But for us, a definition based on the precipitation may be more appropriate. For example, here, if you see the definition based on the precipitation, summer precipitation minus winter precipitation. Here, the green shaded regions are regions where the summer precipitation, summer rainfall minus winter rainfall exceeds 2 millimeters per day. And the yellow shaded regions are the regions where the summer precipitation is less than 1 millimeter per day. So the green regions, green shaded regions are the monsoon regions, and the yellow regions are either deserts or the dry regions. So if you look at the globe, so India comes somewhere here, you can see the Asian region, Asia, South Asia, and the Southeast Asian region, and the Australian region, together called Asian Australian monsoon. So it is a very significant one here. And you can also see the one covering parts of Africa, it's African monsoon. And you can also see parts of America getting the monsoon. But if you see the wind-based definition, you don't figure the American monsoon in this. So now if you look at what causes this monsoon, so one simple thing, if you see, the left panels are the sea surface temperatures and the right panels are the rainfall. The top one is the annual average sea surface temperature and the scales are given here, and the red one, the top one, it is the dark red is the region where the temperature, sea surface temperature exceeds 28 degrees centigrade, very warm water. And if you look at the annual mean precipitation or rainfall, you can see the regions where the warm sea surface temperature is seen, you have more rainfall, which is in the Indian Ocean as well as in the Pacific. You can see the regions where you see more sea surface temperature warming, you get more rainfall. So it strongly suggests the association between the sea surface temperature, warm sea surface temperature, and the rainfall. And this can be more clearly seen in the summer and winter sea surface temperature here. This is summer sea surface temperature, this is the winter sea surface temperature. So what you can see is in summer, this core warming, the strong warming, which is, for example, 29 to 30 degrees centigrade warming, is seen in the north, has shifted to the north with the entire Bay of Bengal and the Western Pacific with very warm water. And if you look at the precipitation, you can also see that the regions where the sea surface temperature was more, you have more rainfall, which is seen in both the Indian monsoon domain as well as the Pacific. And similarly, you can see in winter, the warm sea surface temperature is shifted southward, which is now even south of the equator. And you can see the precipitation also following the system. And this is the rainfall averaged over the Indian longitudes for different latitude. If you see, you can see this is x-axis is for different months, starting from January to December. You can see the peak rainfall in winter happens in February, March, and the peak rainfall in summer happens in June, July. So this consistent in different products, ocean products. And now if you look at the sea surface temperature, you can see the summer hemisphere, the propagation of high sea surface temperature towards the summer hemisphere can be seen here. And the precipitation can be seen here simply following the warm sea surface temperature. So this net radiation, which is showing the similar northward and southward propagation following the summer hemispheres, supports the close association between all of them. You can also see the similar picture in the extent of snow cover, which also plays a crucial role in the monsoon process. Now, if you look at the heating, these left panels are the vertically integrated diabatic heating in summer months at the top, winter months, winter season in the middle panel, and the difference between summer and winter here. And what you can notice is the Indian monsoon domain, South Asian domain, shows very strong vertically integrated diabatic heating. So now if you look at the different monsoon regions, like the Asian Australian monsoon region for the northern summer and the southern summer, you can see compared to other monsoon domains like African monsoon or American monsoon, you can see the Asian Australian monsoon comes out to be the most significant one. Here, the shaded one is the outgoing long wave radiation. The low values of that, the values are, the scale is here. The low values of 190 or less than 200 watts per meter square indicates very strong clouds and convection over this region. So this is in a sense unique compared to the other monsoon regions. And you can also see the winds which are shown in vectors, and the thick red lines are showing the direction of that. You can see the strong cross-equatorial flow towards the Indian landmass starting from the southern Indian Ocean. So which brings a lot of moisture to the region over the Indian landmass. So coming back to the summer monsoon, we have already seen that the Indian summer monsoon is one of the most significant the monsoon. And the summer monsoon is very important for us because it gives more than 80% of the annual rainfall. So the processes which cause the rainfall over the Indian landmass is very important to be studied because the variability of the monsoon rainfall solely depends on the variability in the processes. So if you look at the different processes, there is abundant water available closer to the Indian landmass. You need to evaporate this water, bring the moist air, the evaporated air to the Indian landmass, lift it to the level where it condenses and it rains. So it looks very simple, but we will see that it's one of the very complex processes in the earth system science. So the main components of the summer monsoon are the heat low over somewhere here and the monsoon trough, so which gives a lot of rainfall over the core monsoon region, the central Indian region, and then the Somali jet, which brings a lot of moisture towards the Indian landmass, which is driven by the strong pressure gradient between the southern hemisphere or the winter hemisphere, which is the Mascarean high here, and the heat low over the North Indian region and the Pakistan region. So this drives the winds from the southern hemisphere to the northern hemisphere. The Coriolis force will tilt the flow towards left in the southern hemisphere. That is why you can see some southeasterlies here, which after crossing the equator, they turn right because the Coriolis force now tilt the flow towards right, which brings a lot of moisture towards the land. Now if you see, another important component is the Himalayan belt. So if you see the Himalayan mountain, so they act as a crucial factor in the development of monsoon. They give out a lot of rain over, a lot of orographic rainfall by blocking these winds over here. And another important component is the Tibetan Plateau, which is a long stretch of land with the elevation of about 5 kilometers, which blocks the flow, as well as it acts as a high level heat source, which is also driving the Tibetan anticyclone. And the Tibetan anticyclone is also very crucial because this development of the Tibetan anticyclone, it pushes the upper level tropical easterly jet towards south to create a shear, the vertical shear in the monsoon domain with strong westerlies. So flow from west in the surface level with the flow from east, giving you a very strong vertical shear and good monsoon favorable conditions over the Indian landmass. You can also see some of the features like lows and depressions. You always hear that there are lows and depressions form over the Bay of Bengal, especially the North Bay of Bengal, which are very crucial for the rainfall over this region. So they are also important components. You can also see the movement of the intertropical convergence zone or the strong convection or cloud zones and its northward propagation are important for very crucial for the monsoon rainfall over here, and they are the propagation, the northward propagation is closely associated with the intra-seasonal oscillation of monsoon, that is a MISO, which at a periodicity of 30 to 60 days move north and south, which is the active and break cycle. So when they are active, when the ITCs are over the Indian landmass, you get a lot of rain. When it reaches the foothills of Himalayas, only the Himalayan region, foothills of Himalaya get receive rain, and the other regions we get break-like situations, the situations which we are facing now. And there are other components as well. There are quasi-bi-weekly oscillation of periodicity 10 to 20 days, which brings a lot of moisture to the Indian landmass. Also, the conditions in the Northwest Pacific region, whether the anticyclonic or cyclonic circulation, the main circulation also plays an important role in determining the monsoon here. And the main circulation many times favor the tropical cyclones over this region, especially near the South China Sea region. But the formation of tropical cyclones are going to affect the monsoon flow and the monsoon rainfall over here. So in a nutshell, you can see that it's a very, very complex phenomenon. If you want to look at the monsoon flow, so this is the monsoon flow at a level of about 1.5 kilometer from the surface, and you can see this is about less than a kilometer. You can see that they're very strong and they're persisting, and with an intensity of about more than 10 meters per second. And you can also see the structure. This is the east-west picture averaged over 8 to 15 north, and this is the northwest structure averaged over 50 to 70 east. You can see the vertical extent of the jet, so which is about 3 to 6 kilometer deep. So that is the circulation, that is the moisture which is pushed to the Indian landmass region. And if you look at the mean rainfall, you can see there are a lot of spatial variability with regions such as Western Ghat or Northeast India receiving more rainfall. The scale is here, and regions like the Tamil Nadu or some in the East Coast regions where the rainfall is very less, and the central India and the foothills of Himalayan region receiving more rainfall. So if you look at the standard deviation, so how much they are deviating, because if you want to study the variability, so you have to look at the standard deviation, how much it is deviating from one year to the next other year. You can see the overall all India summer monsoon rainfall deviates about 10% of the mean, but there are regions which deviates even more than that. For example, the regions where you get more rainfall, like Western Ghat or Northeast rainfall, you have more, or Central India, you have more variability. So that is what we are more interested in. So here the variability and the monsoon, mean monsoon for different homogeneous regions are shown for better picture. So you can see the Central Indian region having more variability of about 15. Even the Northwest India also, you can see a lot of variability. And see, as I said before, the monsoon variability is the most complex problem in earth science to model. And you will see why it is so complex. And the remarkable spatial variability can be seen here, and you can also see in the structure of the jet So this is a mean jet. And if you see the different years, for example, I have selected two good monsoon years, 1994 and 2019. You can see the strength and depth of the jet. Whereas if I take two bad monsoon years or deficient monsoon years of 2002 or 2004, you don't see any jet. So this says volumes about the importance of the jet and its dynamics. And if you look at the year-to-year variability in the all India summer monsoon rainfall, so that is what is shown from 1870 to 2019. You can see the black lines here show the average rainfall because they fall between -10 to 10% of the mean. But you can also see there are years which crosses the mean, the standard deviation of 10%. You can see there are years here. So these are the red ones are deficient years and the blue ones are excess years. What you can also see is the circles in red and blue. The red circles are the years when El Nino happens, El Nino co-occurs in the Pacific, and the blue circles represent or shows the formation of La Nina or the opposite of El Nino in the Pacific. So if you closely look at them, you can see the interannual variability in the ISMR is closely related to the formation of El Nino in the Pacific. Though there are years when, like 2004, you can say there are many years, you can see that there are no El Ninos, but still they are deficient. But notice, anything to understand the variability, you need to understand what are they. So if you look at the Pacific conditions, this is the sea surface temperature in the Pacific. If you look at the aerial view, that is the Pacific. What you see in red is the region where the sea surface temperature is high. The region of blue and green, they are the regions where the sea surface temperature is low. So what you can see is the large warm water is seen in the western Pacific during the normal conditions. And this is mainly due to the strong trade winds which push the surface warm water. I need to mention here that in the ocean, the surface water will be warmer than subsurface water because it is heated from the top by the sun. So the trade winds push the warm surface water to the west, and to fill this, the cold subsurface water upwells in the surface. So you can see in the region in the eastern Pacific where the sea surface temperature is very less, and the western region the sea surface temperature is very high. And you can also see what happens, the clouds and convections, this warm sea surface temperature which we have already seen, that the regions where there will be convection and the rainfall. So these convection drives an upward motion, and this also is driven by the downward motion in the cold regions, which together form a cycle called a Walker cell or a convective loop. Now, during this process, a lot of heat is pushed to the western Pacific, which can be seen in, so this is with depth. So what you can see here is the depth where the warm water, that is called the thermocline. You can see a deep thermocline. That means thermocline is the region where the cold water is separated from the warm water. So you can see there is a deep thermocline of about 200 meters in the western Pacific, whereas you can see a very shallow thermocline of 50 meters in the east. So this warm water needs to be pushed away. So that is why the El Nino forms. Basically, the El Nino, which is known as the warming of the East Pacific, East Equatorial Pacific, is a process by which the excess heat accumulated in the Western Pacific is push to the eastern Pacific and the other regions like northward and southward. So now if you look at the and the opposite of El Nino is called La Nina, when the normal conditions becomes more intense with warming, especially confined to the narrow western region. So now if you look at the ENSO indices, so this is very important if you want to know about the El Nino or La Nina. You can see this is the El Nino 1+2 region, this is the 3 region, this is the 4 regions, and this the hashed region. So this is the region of 3.4. So you can see hereafter when I say 3, that's the East Pacific, and 4 is the Central Pacific. 3.4 will be somewhere in between them. And if you look at a vertical slice of the ocean during a peak El Nino phase, you see a very strong warming which is much higher than the surface warming, which is seen at a depth of 100 to 150 meter. So that is the thermocline level. And you can see in the peak time, you can see in the Western Pacific, there is a cooling. So this suggests that the thermocline in the east deepens and the thermocline in the Western Pacific shallows. This is well supported by the sea surface height observed by satellites. So this is the region where the sea level is high. This is the region where the sea level is low, the scale is here. So what you can see is the region where the subsurface warms has the sea level high. The region where the subsurface cools, the region is having low sea level. So now by looking at the satellite picture of altimeter data, you can see what happens in the subsurface. Now this is the typical warming of El Nino, and together with when you have such warming, and this figure shows the sea level pressure. So the warm region, the sea level pressure falls, and where it is cooling, the sea level pressure increases. So with the El Nino formation, there is an oscillation between the pressure at Darwin and Tahiti. So this oscillation strongly suggests, or the relationship between the warming and this index is seen here. You can see whenever the Eastern Pacific warms, you have the oscillation in the pressure index. That suggests that what happens in the ocean has very strong relationship with the features happening in the atmosphere. So what happens in the atmosphere is called Southern Oscillation Index. What happens in the ocean is called El Nino. So El Nino and Southern Ocean Index are very strongly coupled. So this, what you see, is a coupled ocean atmospheric phenomenon. Now if you look at the absorbed winds, sea surface temperature, and thermocline here, so you see a close resemblance between all these variables. So the sea surface temperature is what we use to understand the El Nino, but prior to this is the time scale from 96 to 98. Please note that 97 we have witnessed a very strong massive El Nino. So now prior to this warming, what you can see is the westerly winds. So we strongly suggest that the westerly winds or the wind bursts are responsible for this warming. But what we also can see is the thermocline anomalies, which are positive anomalies. That means they are downwelling waves, so which start propagating eastward. So there's a close correspondence between the wind burst and the SST and the thermocline. And as I said, so this can be seen, the El Nino can be traced because we need to forecast El Nino well in advance. So this is the 1997 January. So the El Nino occurred in summer season, but if you see even in January subsurface, the Pacific subsurface, equatorial Pacific subsurface was warm. You can see in April, the warm anomalies propagate to the east as Kelvin waves, downwelling Kelvin waves, and then by September you can see it propagates, it warms the entire East Pacific, and you can also see there are cooling in the Western Pacific that by January 98 is propagating eastward, but the Eastern Pacific is still warm. The El Nino conditions are very strong here, but what you can notice is these conditions will be immediately followed by the La Nina condition, the cooling, which is seen here, March, and by May you can see the La Nina conditions here. And the conditions are very important because the warm conditions induce a lot of rainfall over here. So this is the wet and warm conditions here, and these conditions induce a lot of dry region in the west and also warm in the western, dry and warm. You can also see warm conditions over the Indian region during winter. And if you look at the same picture in summer, you can also see that the wet conditions in the Pacific, for example, the Central Pacific, but dry conditions you can see in the Western Pacific and the monsoon domain. So this suggests that whenever you have El Nino, you tend to get the dry conditions over the Indian region. So now this is the typical circulation. These circulations are getting changed, and the El Ninos basically change the main general circulation of the atmosphere and make all the changes. So here, the northwest circulation, the meridional circulation, it is seen here. So there is the warm region, the winds or the air goes up or convect, and it subsides in the higher latitudes and comes towards equator, and the Coriolis force will tilt it right. So eventually this blows as a trade winds, what you see here in both the hemisphere here happens. You can see trade winds, and you can also see this is mainly happening because of the differential heating. And in the Pacific, we have already seen the differential heating with the Western Pacific under normal condition with very warm ocean in the west, warm water in the west and cold water in the east, which sort of drives an east-west circulation as well. This is the Walker circulation, which you can see in the other oceans as well. And the Walker circulations get modified or altered during the El Nino conditions. So during El Nino conditions, how the El Nino persists for many seasons is a fundamental question. So what you get is, so the winds here, which are westerly winds, they sort of drives a converging current, ocean currents or the Ekman currents in the equatorial region, which push the thermocline down and propagate eastward as a Kelvin wave, as a downwelling Kelvin wave. So downwelling Kelvin wave, which will push the thermocline down, is favorable for warming in the eastern region. So now when you have warm eastern region, the pressure falls, and the west on the other hand is cool and the pressure increases. So this pressure difference drives again the westerly winds. So in a way, these conditions favor a coupled feedback, which is first found by Bjerknes, and this is called Bjerknes positive feedback. So this positive feedback mechanism drives the El Nino conditions sustained for many seasons. So here the opposite, the La Nina conditions. So here you have the opposite, the easterly winds, which will induce the diverging currents which will induce upwelling Kelvin waves, which propagate eastward and cool the Pacific. And why we are so much interested in this? Because the warm temperature over Pacific has a close association with the temperature over the Indian Ocean. When the Pacific warms, the Indian Ocean also warms. This is a correlation between this, the warming in the Pacific NINO 3 region. You can see that they're very closely associated. That is mainly because when you warm the Pacific region, there will be convection in the upward motion of winds. So the convection or the upward motion will induce lot of subsidence in the Western Pacific and the Indian Ocean. That opens up the sky, that the clear sky will favor more shorter radiation and warm the Indian Ocean. But now if you look at the region, the typical picture of the Pacific warming. So what we have done here is the NINO 3.4 SST. We have correlated with the Pacific, same the peak period, November, December, January, NINO 3.4 value with the same NINO 3.4 region SST. You can see the actual evolution of the El Nino, which is beginning in summer and peaks in winter and then collapse. But what you can see here is the solid line is the correlation of the NDJ NINO 3.4 index or SST with the Indian Ocean SST, with the tropical Indian Ocean SST, that is the 20 south to 20 north, 40 to 100 east SST. What you can see is the Indian Ocean also warms up, which with a lag of few months. But what is difficult to explain by this, the heat fluxes, is the Indian Ocean warming persists even after the Pacific warming disappears. So that is the role due to the ocean dynamics in the Indian Ocean. So if you see how the Pacific signals, how they are transmitted to the Indian Ocean, you can see it's a very strong connection through the Northwest Pacific. So what happens here when you have the heating over the Central Pacific or Eastern Pacific, you can see there will be cyclonic circulation. There will be cyclonic circulation, which is anti-clockwise circulation here, anomalous cyclonic circulation. So this anomalous cyclonic circulation is northeasterly here, and if you look at the trade winds, they are also northeasterly. So these winds induce a lot of evaporation over this region and cool this region. So when you cool this region, there will be an anticyclone forming over this region, so which is the clockwise, in the clockwise direction. So this anticyclone is against the mean circulation, mean trade winds, and so you get warming over this region. And you can also see, as a response to this anticyclone, what you see in the northern hemisphere over the Western Pacific, you see a similar anticyclone in the Indian Ocean as well. So now if you have an anticyclone in the ocean, over the ocean, so that induces a downwelling Rossby wave in the ocean, which propagates westward and warm the southern region. So when you warm this region, the winds from the north, so which will be blowing towards this, again with the Coriolis force, and it's tilting towards right in the northern hemisphere and left in the southern hemisphere. You can see the winds, and these winds continues even in summer months, and these are against the mean winds. So the actual winds reduces its magnitude, and it reduces the evaporative heat loss, and the Indian Ocean basin warms. And once this Indian Ocean warms, you can see the anticyclone, what we see here in the Northwest Pacific, extends even to the Indian region. So the anticyclone which is extending to the Indian region, which affects the monsoon over the eastern region where it is extended. And you can also see this warming excites the warm Kelvin waves, which is also inducing a lot of cyclonic circulation, and they in turn gives a lot of rainfall over the southern part, especially over the western Ghat region. So now you can see these processes, for example, the ENSO, and this process co-occurs with another process, another mode of variability in the Indian Ocean called Indian Ocean dipole. So which you can see them together. So the ENSO happens in summer, and it lasts for the next summer, about a year. And what you see, the Indian Ocean dipole, which peaks in September, and which is followed by basin scale Indian Ocean warming, which sort of fade back, or there's a coupling, strong coupling between the Northwest Pacific anticyclone and the Indian Ocean warming. So they together drives the entire monsoon variability over this region. So now if you look at this, the Rossby wave dynamics, you can see the winds here associated with IOD or the El Nino will be easterlies here. These easterlies here will push the surface water poleward, northward in the northern hemisphere and southward in the southern hemisphere, which creates a lot of downwelling over here. You can also see already the basin is driven by the anticyclone here as a Rossby wave. So the Rossby wave formed here is intensifies, and this helps to sustain the warm waters of the Indian Ocean for several months. So you can also see that these Rossby waves, they drive a very strong north-south mode in the Indian Ocean subsurface, which lasts for several seasons and assisting a warming in the Indian Ocean. And this also supports a very strong mode of asymmetric winds and precipitation and rainfall and pressure, creating a very strong warming of the Indian Ocean. So please also note that this is the correlation between the thermocline and sea surface temperature. You can see they are very well correlated, which suggests that the subsurface warming in this region is going to affect the surface warming over this region. And such warming over this region is very, very important for the monsoon variability over this region. And you can also see that this is the cross-equatorial flow, which is towards the summer hemisphere or the warm hemisphere. That means the atmosphere, you can see a lot of heating towards the north, but to balance that, ocean on the other hand push the water southward. So you can see during the southwest summertime and winter time. See, summertime the ocean tries to cool by pushing the water southward, and in winter time the ocean tries to warm by pushing the water northward. And you can see the summer strong monsoon, for example, during the strong monsoon years, you can see the winds are strong, so they will induce more southward flow of warm ocean water, so the ocean will cool. The northern ocean will cool during a strong monsoon year, and a weak monsoon year, the southward heat transport will be less, so which sort of warm the North Indian Ocean. So this, in a way, acts as a biennial, the 2-year cycle in the Indian Ocean itself. And as I said, the Indian Ocean dipole, so which is the second dominant mode of variability, which is this mode. But I said as a response of ENSO, which is coupled with a lot of processes in the Indian Ocean, which is the leading mode of variability, and this is the second mode of variability. And these variabilities are very closely associated with monsoon, and so very important for Monsoon, because as you see here, so they are closely associated with the circulations and clouds over this region, which you can see on a positive IOD period, the eastern Indian Ocean cools, the western Indian Ocean warms, and the clouds are shaded in white color. You can see the west, there are more clouds and convection, which is also seen over the Indian landmass, and you can see that the positive IOD is favorable for more rainfall over here, and a negative IOD suppresses the rainfall over the Indian region. And what you see as a comparison of the Pacific and Indian Ocean, there is a close association between the El Nino in the Pacific and the IOD in the Indian Ocean, though IOD is a very short-lived feature. So here there are westerly events, they drive the downwelling Kelvin waves. In the Indian Ocean, there are easterly events, they drive upwelling Kelvin waves. And you can see there are cyclonic curl here, cyclonic shear induced curl. So that will induce upwelling over here of the equator in both the hemisphere, and they propagate westward as a Rossby wave. So the warm Kelvin wave move eastward, and the cold or upwelling Rossby waves propagate westward. Similarly, in the Indian Ocean, there will be the upwelling Kelvin waves which moves eastward and cool the eastern region, and the anticyclonic, the shear-induced Rossby waves, the downwelling Rossby waves, they move westward and warm the western region. And you can see the equatorial winds are closely associated with these processes. And if you see the equatorial wind index, which when you compare with the rainfall, so these are different years based on the excess or deficit ISMR years. So you can see the deficit years in the beginning to the excess years. You can see the green ones are the Indian summer monsoon rainfall, and the orange ones are the equatorial winds in the Indian Ocean, and the red ones are the convection over the Pacific, Central Pacific. You can see the Indian monsoon rainfall is very closely related with equatorial winds. So this strongly suggests that understanding the equatorial dynamics is very, very important to understand the variability in the summer monsoon, Indian summer monsoon rainfall. You can also see the Indian Ocean dipole and the equatorial winds are closely related with a correlation coefficient of 0.73. Also, you can see the dipole mode index and the El Nino are closely connected. And so what we have discussed till now are the processes which can cause the large scale year-to-year variability in the monsoon rainfall. So, but monsoon rainfall also vary from one decade to another decade, or one epoch to another epoch. This is mainly caused by two gigantic phenomena such as Atlantic multi-decadal oscillation, which is showing few decades of warming and few decades of cooling. And similarly, there's one in the Pacific called the Pacific decadal oscillation, which you can see the warming in the north and the East Pacific and the cooling in the west. So this, you can see the different phases here. This is the cold phase. You can see cooling here and warming here. This is the warm phase, warming here and cooling here. What you can also notice is this, the decadal scale phenomenon is very closely tied with the tropical variability, which is called El Nino, and its response to the Indian sea surface temperature over the Indian Ocean. So in a way, all these processes in the decadal scale are connected to the tropical variability, which we have already discussed. So anything which we talk about that or forecasting or the predicting the monsoon, all these multi-decadal and decadal timescale variability play important role. Now, if you see the warming over this region, warming over the North Atlantic, if you correlate with the rainfall, you can see there's a contour which are rainfall. So you can see a lot of positive rainfall over the Indian landmass. So the warming over the positive phase of the AMO, you tend to get more rainfall, and the negative phase of the AMO, you get less rainfall. Similarly, you can see the PDO index. So that is the leading mode of variability in the North Pacific. If you see the eigenvalues of the covariance matrix formed by the sea surface temperature over here, you can see the dominant eigenvector, so which is the empirical orthogonal function, so which if you correlate with the rainfall, you can see there's a negative rainfall over the land region during the positive phase of the PDO. So positive phase of the PDO, it is quite understandable because the positive phase of the PDO is in phase with the El Nino conditions in the Pacific, which is not favorable for good monsoon over the Indian landmass. So this is the close association with the Pacific decadal oscillation or interdecadal Pacific oscillation, and the ENSO. You can see there are a lot of similarities between them. The only difference is this happens in decades. This happens from one year to the other year. So this is the Atlantic multi-decadal oscillation, which has a scale of 30 to 60 years. You can see there are over 30 years of positive phase and few years of negative phase and positive phase and negative phase. So they all have strong impact on the monsoon. You can also see this is the power spectrum of the PDO and the El Nino or ENSO. You can see this peak it corresponds to 3 to 4 years of the peak variability, which is the interannual variability. This is the decadal variability, the multi-decadal variability. The thick line is ENSO, which shows both interannual and decadal. So that means the ENSO itself is showing a decadal variability, and the PDO, which is a multi-decadal phenomenon, which is also showing a decadal variability and a weak interannual variability. So all these things, the evolution of all these things are very important to be understood for understanding the monsoon variability. Now, all these relationships are changing in the recent years. For example, so this is the figure. The red one is the vector. The leading mode of variability or the principal component associated with the leading mode of variability, which talks about the evolution of the PDO or IPO. And this is the similar evolution of subsurface temperature in the Indian Ocean. What you can see is there's a correspondence between what happens in the Pacific and what happens in the Indian Ocean, with the Pacific driving this. But if you notice in the recent years, for example, after 1990s or so they are in the opposite phase. So for example, the Pacific variability in the positive phase, the Indian Ocean variability is in the negative phase, and that continues. So the understanding and the relationships between these modes and the monsoon are changing. So this needs to be accounted to make any forecast of monsoon, because the impact of them will be totally different. For example, you can see this is the correlation. For example, the Indian Ocean winds correlate with the Pacific winds. You see the period 68 to 93 is one period when you have a positive correlation, but the same Indian Ocean winds with the Pacific winds, if you see, they are opposite. So that is what I said, the relationship between the Indian Ocean and the Pacific are changing. And so our understanding has to be carefully interpreted for making any forecast. See, another complex feature of the complete process, for example, the El Nino, is the years like 1998, 1997, 98 El Nino, you can see the warming starting from the East Pacific. So this we call it cold El Nino or a Eastern Pacific El Nino. And if you see the year like 2005, for example, so you can see the warming you can see in the Central Pacific or the Western Pacific. So this type of Central Pacific warming is called Modoki or El Nino, or Central Pacific El Nino. Sorry, this is El Nino Modoki. And you can see similar changes or flavors of El Nino from year to year. So the El Nino structure is not consistent. So the impact of them on the Indian monsoon or the Indian Ocean will be different. So this is the sort of warming in the Pacific Ocean, see, during different years. You can see the Pacific warms at different places and different intensity. This is the intensity and this is the location. These are from the West Pacific to East Pacific. You can see they're warming at its own wish. So the warming over here and warming over here and warming over here will have different impact on the monsoon. So that has to be incorporated very well in the models. The model should capture this type of variability to predict the teleconnections or the remote connections. And you can see the same picture. The one is the Nino and the Indian monsoon. So there are years when the El Nino affects the monsoon. So here in this box, red box shows the El Nino affecting monsoon, because you have El Nino which is positive, the monsoon is negative. But there are years when El Nino is positive, but the rainfall is positive. So the relationship is not preserved. So it is not a permanent relationship. So it's a time varying relationship that has to be accounted very well for forecasting purposes. And you can see the leading mode of variability. If you see the first mode, which shows as the East Pacific El Nino, but if you see the second mode of variability in the sea surface temperature, you can see the Central Pacific is warming and the East Pacific is in fact cooling. So which is totally different from the pattern of the typical El Nino. And you can also see these relationships are very complex and in very coupled to different modes of variability. You can see the PDO, which we discussed before, so which is very closely associated with the Aleutian low, and that in fact the Kuroshio extension, meridional mode, and they again fade back. See, it's also seen that the El Nino Southern Oscillation, which through the atmospheric connection or vapor circulation changes we have seen, so which can also affect all these modes of variability and in a way feed back to the PDO. Similarly, you can see the different modes of the Pacific, how the mid-latitude variabilities feeding back to the tropics and the tropics feeding back to the mid-latitude variability. So all these are important phenomenon, and you can also see the El Nino monsoon relationship for different periods. For example, this is prior to 1976. When you have a El Nino, you get a negative relationship, whereas in the years after 1976, you can see a positive relationship over the region where you get more rainfall. So the relationships are changing. This is the monsoon period of the year when the El Nino forms, and these relationships follows in the next year as well, with the more positive over this region in the following year. And you can see in the recent years, this is the correlation with the Indian Ocean SSTs, which are negatively correlated in the period before 1976, now is positively correlated. So the time varying features are important. And these are the tropospheric temperature, the upper tropospheric temperature. You can see as a response, the tropospheric response to the Pacific heating as a Rossby wave response, you can see. So they play an important role in modulating the monsoon during these two periods. You can see they are completely different. For example, what you see along the equator is a Kelvin wave response. What you see in the north and south are Rossby wave response. You can see the extent of response in the recent years are different. That is mainly because of the timing of the El Nino and the location of El Nino. And you can also see what it changes. See, for example, the years before 1976, these Kelvin waves, they travel all the way in the Atlantic and they come back to Indian Ocean, and you can see a response which is warming over the Indian Ocean and a cooling over here, which sort of weakens the pressure gradient and weakens the monsoon, whereas in the recent years such gradient or the weakening of gradients are not seen. So these are all very important processes the models, the forecasting models should capture. So the monsoon prediction is depending mostly on how we predict the El Nino, because 50% of the monsoon variability or predictability comes from ENSO. So we need to predict ENSO very, very well. The current climate models over-predicts ENSO, and its impact on monsoon is also over-predicted. So such issues need to be resolved before we make the models, before we use the models for forecast. And also we can see that you can see this picture of the recent years, there are anomalous evolution of and midway termination of both El Nino and La Nina takes place. So they are not well captured by the models. And another important problem is the complex interaction between the PDO and ENSO, which we have seen in the previous slides, which are not clearly understood. This needs to be understood very well to make meaningful forecast. See, another issue is the monsoon variability. What happens to the monsoon variability in the near future, the next 50 years or 100 years? So now we use the climate projection models to understand them. So what we see is the most models predict a modest increase in interannual variability. That means the deficient or excess of the intensity of deficit and excess will increase in the near future. And also what we have seen in the models of the frequency of heavy rainfall events increase. And since El Nino has dominant influence on monsoon variability, the accurate prediction of El Nino remains a crucial component. The PDO and IPO under warming climate dominates mostly a decadal nature instead of a multi-decadal nature, which breaks the relationship between the Pacific and the Indian Ocean. So that needs to be captured by the models. So the PDO is strongly coupled to the Indian Ocean when they have multi-decadal nature, but they are not strongly coupled or oppositely coupled when they are not in multi-decadal nature or the decadal nature. See, Indian Ocean in the recent years weakened its relationship. So these all are crucial factors which needs to be taken into account when we make the forecast. So this is the summary of my talk. And with this, I thank all of you for attending this lecture. So now I will take questions.
Thank you, Dr. Seelan, for a wonderful basic talk on monsoon variability and many basics and very good schematics, etc. A lot of overwhelming questions are there, so a few of them I have kept for you. You can kindly answer this.
The first question is how Southwest or Indian monsoon is different from Asian monsoon. is the global warming showing impacts on Indian monsoon? Yes, as I showed you in the beginning, the southwest or Indian monsoon is different from the other monsoon. You can see in all aspects the characteristic features and the orography. You can see the regions of orographic rainfall, regions of the convergence driven rainfall, so which are different from the East Asia or the other Asian region monsoon. The second question is the global warming showing impacts on Indian monsoon. Yes. So what we have seen, if you believe in the models which are projecting under the global warming scenario, the models show moderate amplification of the interannual variability of the Indian summer monsoon. The next question, how the Atlantic Ocean sea surface temperature affects the Indian monsoon rainfall? Is there El Nino-like effect in the Atlantic Ocean? I will answer the second part first. Is there El Nino-like effect in the Atlantic Ocean? Yes. There's El Nino, there's an Atlantic Nino, which is an oscillation you can see in the Eastern Pacific, but that also like a positive phase of the Atlantic Nino, which is a warming over the Eastern Pacific that affects the monsoon, whereas the North Atlantic AMO, Atlantic multi-decadal oscillation, a positive phase, you get a positive rainfall. The excess rainfall that is mainly due to modification of the low-level jet and the equatorial processes in the Indian Ocean. The next question is why El Nino and La Nina are not symmetric in terms of their spatial structure, evolution, and teleconnection. That's a very good question. So answer, I need more time to explain. So I will try to explain it in a simple way. I told you the El Nino is a process of removing the heat. La Nina is a process of rebuilding the heat. As you know, rebuilding takes time. The La Nina is a long process and spending is very easy, as we know. So the El Nino is actually spending the heat accumulated by La Nina. So that explains. I know this is not a very convincing answer, but there are many other mechanisms as well, which I need more time to explain. So if anybody is interested in understanding this in detail, they can write to me directly. So this needs more than a lecture to explain that. And now, next question, between a coexisted El Nino and a positive IOD, which has a more impact on Indian summer monsoon precipitation change? So that is also a very, very, very good question. So very, very difficult to answer, but I will try to say that the El Nino is a massive variability compared to the Indian Ocean dipole. So what I strongly believe is the El Nino will have more effect on the monsoon, but more than the Indian Ocean dipole, what I see is the equatorial winds and the equino, they are more closely related to monsoon because the IOD evolves little after the monsoon season, or it is towards the end of the season. The IOD peaks in September or October. So by the time we are done with the monsoon rainfall, so I can say they are the Indian Ocean winds. But if I say that these equatorial winds are not only driven by the Pacific, it is also driven by the IOD. So what actually affect monsoon is a sort of combined effect of the El Nino and IOD driven equatorial Indian Ocean winds, which plays dominant role in controlling or amplifying or suppressing the monsoon. And the next question is why PDO or AMO or decadal but ENSO and interannual variability. If you look at the processes, though the formation of PDO and AMO, the mechanisms are not completely understood, but the coupled processes which are understood till now is a complex interaction between many modes of variability in the Pacific and Atlantic, which are responsible for the PDO. For example, the Aleutian low, the Kuroshio-Oyashio extension changes, the oscillation of wind, pressure. All these things are connecting the PDO, and it needs time to evolve. So that is why you have a decadal or multi-decadal scale to evolve this variability. Similarly, the Atlantic multi-decadal oscillation, which has very close connection with the ocean currents, the meridional overturning circulations of the ocean. As you know, the ocean currents are very, very slow process, which takes years and decades to complete the oscillations. So that is why the PDO and AMO are decadal, whereas ENSO is an interannual variability. And thank you so much for the question. And if you have any questions, please, and these are the questions I could see in the chat mode. And if you have any more questions, please do write to me. And thank you so much for watching the live talk.
Thank you, Dr. Sheelan, for answering the questions. On behalf of MoES webinar, we thank you for sparing your time with us. So now we can go offline. Thank you very much.
Thank you.